Assalamu alaikum friends. I am Taqdees Ahmed Siddiqui with Computer Graphics for Bachelor's in Computer Science course being offered by Virtual University, Government of Pakistan. Today is our 41st lecture. Today we shall be talking about some aspects of viewing and modeling using OpenGL. So let's begin. Today we shall practically implement viewing a geometric model in any orientation by transforming it in three-dimensional space and control the location in three-dimensional space from where the model is viewed. Whenever we'll talk about modeling and viewing, we shall be taking the perspective of a camera looking at a scene. The very way we are photographing some scene and we make use of our camera in order to adjust the view, whatever model is our center of attention that we want to look at, that we want to photograph, that has to be covered from the desired angle. So all those aspects would be covered in today's lecture. Also we shall see clipping some undesired portions, modeling transformation, projecting the model, and then combining the transformations. These are the things that we have developed the basis of. Today we shall be putting them together in order to come up with the final form. We shall also discuss on how to instruct OpenGL to draw the geometric models. Now we must decide on how we want to position the models in the scene, and we must choose a vantage point from where to view the scene. For this we can use the default positioning and vantage point, or we can specify position and vantage point the way we want it. And then we have to choose a viewpoint. There is the concept of some default viewpoint or vantage point, and that can be used, or if required, if our requirement of the scene is that we want to place our models the way we want them, we want to choose a specific viewpoint, we are also allowed to do that. We can make use of available routines that can help us come up with a different viewpoint. Whenever we are talking about displaying or showing a scene, it is analogous to photographing. As I said earlier as well, तस्वीर जब आप बना रहे होते हैं तो आप देखते हैं कि आपको कौन सा ऑब्जेक्ट है जिसको कैप्चर करना है, and how you want it to be appearing. Do you want a close-up of it, or you want a distant look? Where you would like to place the camera? Do you want to be at the height of the model, or you want to be at certain elevated point, or lower the elevation? So all those things that we have to take care of while photographing, they'll have to be taken care of while we are talking about modeling and viewing using the OpenGL. So very much preparation would be required on part of the programmer as to what kind of appearance is required for the models in the scene. If we want to look at the corner of the room containing a globe, for instance, then we must decide how far away from the scene is the viewer and where exactly should the viewer be. So we have to make a decision that if we are going to look at a specific corner of a room that contains some model, we have taken the example of a globe, for instance, what is the view that we want? Do we want a close-up of the view, close-up of the globe, or we want it along with certain other details that could be a part of the floor as well, maybe, or at times maybe part of the ceiling that we want to show. So depending upon what we really want to project, what we want to show, we'll have to decide where the viewer is likely to be. Where should we place our camera so that the view that we capture, that should be able to communicate what we actually want to communicate using that scene. So we would be working on those lines while planning and preparing the programs using OpenGL. We would like to ensure that the final image of the scene contains a good view. For instance, if a portion of the floor is required to be seen, that should be visible. All the objects in the scene are visible that are required to be present in the scene. And the objects are presented in an interesting arrangement. That's also important. As I have been saying earlier as well, that we would be acting like a photographer. So we'll be seeing what kind of looks we want and what would be making our scene more interesting. we have to keep a balance of all those things. We would not like to have an imbalanced view. We would not like to have some certain objects that are maybe required to be visible, but they are only partially visible in our scene. We'll have to cover them all. And in order to make sure that all those objects or model parts are viewable or visible, we'll have to place our camera accordingly. We'll have to decide about the point from where we are going to view the scene accordingly. And that will have to be specified using some instructions to OpenGL. Now we'll see how we can use OpenGL to accomplish these tasks that are at hand. How to position and orient models in three-dimensional space. How to establish the location in three-dimensional space of the viewpoint. We need to answer these questions. Of course, part of this arrangement would be positioning and orienting our models at the right direction and the right view in the three-dimensional space that would be captured thereafter from the decided viewpoint again in the three-dimensional space. Whenever we are talking about 3D, we are talking about both objects and the viewer taking some position in the three-dimensional space. So we can have the concept of some objects which are sitting on the origin maybe, and we have our viewer somewhere in the three-dimensional space. Or we could have another scenario in which the viewer is at the origin and our objects, they are elsewhere. And from the object we are looking at those, from the origin we are looking at those objects. So whatever the scenario may be, we have to plan it, we have to chalk it out, and we have to make a decision on where to place the objects and where to place our viewpoint, or where to place the camera for that matter. All of these factors help determine exactly what image appears on the screen, because ultimately what we want is an absorbing, interesting image. Although ultimately a two-dimensional image of a three-dimensional model is drawn, yet we need to think in three dimensions while making many of the decisions that determine what gets drawn on the screen. We already know that whenever we are talking about some three-dimensional object, even then, when it is to be displayed, तो display का image जो है वो तो हमें two dimension के अंदर ही बनाना पड़ता है, because our display device has limitations. So जब हम three-dimensional object को two-dimensional image की form में ही display करने जा रहे होंगे, तो फिर हम क्यों ना सारे काम 2D में ही करें. But the idea is that the whole processing of thought process of coming up with the model, orienting the objects, positioning the viewpoint, and then coming up with the required scene, that has to be perceived in three dimensions. अगर इस सारे के अंदर हम थ्री डायमेंशनल व्यू का ख्याल नहीं रखेंगे, तो फिर अल्टीमेट हमारा जो व्यू होगा सीन का, वो रियलिस्टिक नहीं बनेगा, वो उस तरह से अपेयर नहीं होगा जैसा हम चाहते होंगे. फॉर इंस्टेंस, अगर हम इसी थ्री डायमेंशनल स्पेस के अंदर उसी सादा सी एग्जांपल की बात करते हैं कि कॉर्नर में एक टेबल के ऊपर हमने ग्लोब रखा हुआ है, एंड वी वांट टू शो दैट, वेल, लुकिंग एट दैट ग्लोब और दैट ऑब्जेक्ट फ्रॉम डिफरेंट एंगल्स विल बी प्रोड्यूसिंग डिफरेंट व्यूज. एक व्यू ऐसा होगा जिसके अंदर हमें टेबल के 3 साइड्स दिखाई दे रही होंगी. 2 साइड्स जो हमारे कॉर्नर की साइड पे बनते हैं और इसकी टॉप दिखाई दे रही होगी, और उसके ऊपर फिर हमें ग्लोब पड़ा हुआ नजर आएगा. लेकिन ऐसे व्यूज भी हो सकते हैं जिसके अंदर हमें टॉप दिखाई ना दे. देयर स्टिल कैन बी अनदर व्यू जिसके अंदर वो साइडें जो है वो नजर ना आए. वी माइट पॉइज आर कैमरा एट द टॉप. व्यू पॉइंट हम ऐसा सेट कर लें कि हमें सिर्फ ग्लोब और टॉप ऑफ द टेबल दिखाई दे रहा हो. So depending upon what we want to achieve, we have to think in 3D. So ये modeling का काम जो है हमें करना 3 dimensions में ही पड़ता है. Ultimately जब उस 3 dimensional view को हमने मैप करना होता है onto our display device, so उसका 2D image बनता है. Pixels की form में उसको हमें represent करना पड़ता है, and then only we are able to show that image or display that image. But regardless of that, we have to think in 3D in order to come up with a realistic model and then a realistic view of that model. A series of 3 computer operations converts an object's 3-dimensional coordinates to pixel positions on the screen. Transformations, which are represented by matrix multiplication, include modeling, viewing, and then projection operations. Whenever we will be talking about displaying some object, we'll have to go through these steps. We will be modeling, we'll be deciding what object or objects need to appear in the scene, at what angle each of those objects would be poised in the scene, and then how we are going to view them, where would be our viewpoint, and of course we would also be deciding what type of projection operations we want to perform. We have already covered the basic concepts of different types of projections, mainly segregating them as parallel and perspective projections. So we'll be deciding what type of projection we are going to use to project that scene. We'll be modeling, we'll be deciding about the viewing specifications, and we'll be deciding about the projection to be used. Such operations include rotation, translation, scaling, reflection, orthographic projection, and perspective projection. And generally we use a combination of several transformations to draw a scene. We have been talking about transformations and combinations of transformations earlier on as well, while we were talking about the 2-dimension and then the 3-dimensional modeling in space. We have had our discussion on transformations, which include all these basic types that we are going to cover today as well. So we will be combining these transformations to come up with our final required orientation of objects, and hence the scene as well that we want to project. Since the scene is rendered on a rectangular window, objects or parts of the objects that lie outside the window must be clipped. In 3-dimensional computer graphics, clipping occurs by throwing out objects on one side of a clipping plane. We have talked about issues involved in clipping, but the basic concept is the same, that since our ultimate image would be appearing in a rectangular window, we better take care of such objects or parts of objects which are not to be included in our scene, in our view, and they have to be clipped. So that clipping process would take place for those objects or parts of objects that are lying outside our scene. More or less वही तरीका है जिस तरीके से हम कैमरे से तस्वीर बना रहे होते हैं. We have to cover the objects of interest only, and we clip using certain methods whatever is undesirable, whatever we don't want in the scene. ये काम 2-3 मुख्तलिफ जगहों पर होते हैं, उनका जिक्र हम आगे चल के करेंगे. Finally, a correspondence must be established between the transformed coordinates and screen pixels. This is known as the viewpoint transformation. In the viewport transformation, what we do is that we map the model that we have come up with onto the screen pixels. So whatever image is required to be displayed would be displayed in the form of pixels on the screen. So we have to have a correspondence developed between whatever coordinates we have come up with for the objects or parts of objects in the scene that would be mapped onto our viewport, where they would be ultimately displayed. So this step would be termed as the viewport transformation, and we have OpenGL helping us in this area as well. Now we are going to take an analogy. We have already started discussing use of camera and the way we photograph different scenes, and trying to relate it to the way we model our objects or views in 3 dimensions using OpenGL. So we're going to take this analogy to help us better understand what is desired of us as programmers to think or pre-think before we walk into programming our scenes. The transformation process to produce the desired scene for viewing is analogous to taking a photograph with a camera. As is shown in the next figure, the steps might be these. The first one, of course, the foremost step would be to set up our tripod pointing the camera towards the scene. And this can be termed as our viewing transformation. जैसा पहले भी कहा कि इससे पहले कि हम शुरू करें तस्वीर खींचना, सबसे पहले हमारा काम यह होगा कि हम कैमरे का रुख उस तरफ करें जिस तरफ हमारा ऑब्जेक्ट ऑफ इंटरेस्ट है. So the very first step that we have to perform is set up our camera in such a manner that the camera is looking at the very scene that we want to capture. Let's take it to be the most primitive step in this. The next is to arrange the scene to be photographed into the desired composition, and this would be termed as the modeling transformation. Second, choose a camera lens or adjust the zoom, and this would be analogous to the projection transformation. कैमरे को इस्तेमाल करते हुए हमने कंपोज करना है जिस सीन को, उसके अंदर जो चीज़ें हमारे जो ऑब्जेक्ट्स ऑफ इंटरेस्ट हैं उनको किस तरीके से ऑर्गेनाइज करना है, दैट वुड बी पार्ट ऑफ इट. आप तस्वीर खींचने जा रहे हैं और आपने से एक ग्रुप फोटोग्राफी बनाना है. व्हाट डू यू डू? You arrange the objects in a desired fashion. If you see that there are a few people who are longer or taller than others, you ask the taller people to take the row behind the shorter people. A way of composing the picture. Or you arrange different people wearing different types of outfits accordingly in the scene. Whatever is the desired results, according to that, you arrange your model, your objects in the model. And that would be part of the modeling transformation. And we would also be adjusting the camera lens or adjusting the zoom in or out depending upon how closely we want to look at the objects in the model, and that would be our projection transformation. We have seen that different types of projections tend to result in different types of views of the same scene. So depending upon what is required, we would be adjusting our projection transformations. Next step is to determine how large we want the final photograph to be, because we might want it to be a very enlarged view, and this would be the viewport transformation. In case of ordinary camera, when we are using, we have captured a scene, but ultimately how big do we want the print? That is decided thereafter. But it is part of the consideration. Before we get the final image, this has to be decided. So this decision will be made, and this would be coming under the viewport transformations head. And the next step would be that all these steps, having performed them, the picture now can be snapped or the scene can be drawn. Picture would be snapped when we are using the camera, and the scene would be drawn when we are talking about programming. The illustration that you have on your screens right now is going to assist you to understand this camera analogy. This is comparing how we'll be performing these basic steps when using a camera or when using a computer program to come up with the scene or the final view. In the first one, the left hand side is showing what we'll be doing with the camera. We'll be adjusting and setting up our tripod with the camera in such a manner that the camera is looking at the scene that we want to capture. The objects that are desired to be snapped, they have to be covered in the view of the camera. So camera का मुंह हम उस तरफ कर देंगे जिस तरफ हमारे desired objects हैं. But in case of OpenGL programming, we would be performing our viewing transformations. We'll be positioning the viewing volume in the word coordinates that we want to capture. And the next one would be to find the model, orient it the very way we want to capture it using the camera. In case of programming, we'll be modeling in here, positioning the model in the word where we want it to be and whichever way we want it to be. If we want to rotate it, we do that. If we want to displace it by a certain distance, we do that. And all that would be part of the modeling transformations. And physically, when we are taking snaps using the camera, we'd again be using the same analogy. Whatever the object may be, we'll be adjusting its orientation in order to come up with the desired view, which can be snapped at the end. In the next step, we use our lens to zoom in or zoom out or decide about how our view would be captured in the snap, and that part is taken care of in the projection transformations, where we are determining our viewing volume or viewing frustum, what shape it would be, what size it would be. We have talked about this idea that whatever falls outside the viewing frustum is not visible in a scene. And finally, in case of photograph, we would be deciding what size of blow up we want, कितनी enlarge करनी है तस्वीर या छोटी बनानी है, और के पैरेलल जो काम हम यहाँ पे करते हैं OpenGL programming में, that would be the viewport transformations, which will be telling us, okay, आपने मॉडल कर लिया, आपने अपना व्यू भी सेट कर लिया, अब फाइनली इस व्यू को जब आप प्रोजेक्ट करेंगे ऑनटू द स्क्रीन, ऑनटू दैट रेक्टेंगुलर विंडो, तो उसमें क्या क्या कुछ किस तरह से दिखाई दे रहा होगा, and that would be done as the last step. So that is how we compare and actually relate the two processes of taking a photograph using a camera and coming up with specifications and details of a scene using OpenGL. Note that these steps correspond to the order in which we specify the desired transformations in our program, not necessarily the order in which the relevant mathematical operations are performed on an object's vertices. This will have to be carefully noted that it's not necessary that the execution of those commands resulting in some transformation changes on the vertices of our objects of interest, that takes place in that very order in which we specify our transformations. The two orders can be different from each other. We'll be taking a closer look at it, and we'll be able to develop some better concept of the same idea pretty soon. The viewing transformations must precede the modeling transformations in our code, but we can specify the projection and viewport transformations at any point before drawing occurs. Figure 2, which is coming up next, that shows the order in which these operations occur on our computer. So what we need to note is that whenever we'll be writing programs, we have to make sure that our modeling is done after our viewing transformations have been specified. So the viewing transformations should come first, and thereafter we should specify our modeling transformations. Whereas the other two, the viewport transformations and the projection, they are immaterial. Their order is immaterial. They can be specified anywhere before we finally draw our scene. But we have to make sure that when we are talking about the viewing and modeling transformations, their order must be viewing transformations first and then followed by the modeling transformations. Currently, you are looking at different stages of vertex transformation. We are starting with the object coordinates. Here you are seeing them as x, y, z, w. They go through the first step, which is model view matrix, and as a result, the output that we get from this is the I coordinates. These I coordinates walk into the projection matrix, and the resulting output is clip coordinates. These clip coordinates then go through the perspective division. Output of this step is normalized device coordinates. And finally, we perform the viewport transformations, the resultant of which would be the window coordinates. So these are the stages that vertex transformations would go through. The original vertices, they would be processed in this order to come up with I coordinates, clip coordinates, normalized device coordinates, and then finally the window coordinates, which are actually used to display our scene in the output window or viewport. To specify viewing, modeling, and projection transformations, we construct a 4x4 matrix M, which is then multiplied by the coordinates of each vertex V in the scene to accomplish the transformation V dash equals MV. Thus far we have been talking about different types of transformations, और सबके अंदर हम आसानी के लिए, कैलकुलेशंस की आसानी के लिए ये जिक्र करते आ रहे हैं कि हम इनकी ज्योमेट्रिक या मैथमेटिकल फॉर्म्स को मेट्रिसेस की शक्ल में, मैट्रिक्स ऑपरेशंस की शक्ल में एक्सप्रेस कर सकें ताकि हमारी प्रोसेसिंग आसान हो सके. यहाँ जब आप OpenGL का इस्तेमाल करेंगे, then you would realize and you would appreciate that how those concepts are really going to come handy. Expressing or being able to express different transformations as matrix operations really helps us. Whenever we want to perform some transformation, we want to translate an object, what we need to do is we specify the translation vector, specifying how much we want to move along x-axis or y-axis or z-axis, and making use of those values we come up with our translation matrix. having set up the translation matrix, we specify that as a matrix multiplication, a matrix holding the vertex of interest and a matrix holding the translation matrix, and the two are multiplied together to come up with the translated vertex. That is the basic principle that we are going to follow for all transformations. So here again we are talking about one 4x4 matrix, which would be a standardized matrix in order to hold all different types of transformations that we would be interested in using for vertices of our objects in the scene, and then we will be performing matrix multiplications. Remember that vertices always have 4 coordinates, x, y, z and w, though in most cases w is 1 and for 2-dimensional data z is 0. Also note that viewing and modeling transformations are automatically applied to surface normal vectors in addition to vertices. Here I am just helping you recall that we have already established the concept of homogeneous coordinates when we were talking about 2D transformations and then later on 3D transformations. So every 3-dimensional point is not given by only 3 coordinates, the x, y and z, but w is also there, which is the homogeneity factor. We have also standardized this process, specifying that factor to be 1, w to be equal to 1, so that our processings can be really simplified. But nevertheless, w is there, and whenever we will be talking about 2-dimensional, we will be talking about a z value equal to 0. Normal vectors are used only in I coordinates. This ensures that the normal vector's relationship to the vertex data is properly preserved. We have talked about the concept of the surface normals and the vertex normals, and we have been effectively using them in order to simplify our calculations. And you'll see those concepts are going to come handy over here as well. The viewing and modeling transformations we specify are combined to form the model view matrix, which is applied to the incoming object coordinates to yield I coordinates. Next, if we have specified additional clipping planes to remove certain objects from the scene or to provide cutaway views of objects, these clipping planes are applied. क्लिपिंग प्लेन्स का कॉन्सेप्ट यही है कि वो ऑब्जेक्ट्स जो कि हम चाहते हैं कि हमारे सीन में से एलिमिनेट हो जाएं, उन्हें हम आइडेंटिफाई कर लेते हैं और उनको उन प्लेन्स में स्पेसिफाई कर देते हैं जिनको कि हम क्लिपिंग प्लेन्स कहते हैं. दोज प्लेन्स whatever they contain gets clipped at the end of the day, and the objects that lie in those planes, they do not appear in our final scene. After that, OpenGL applies the projection matrix to yield clip coordinates. This transformation defines a viewing volume. Objects outside this volume are clipped so that they are not drawn in the final scene. This idea we have also talked about from the perspective of specifying viewing frustum. So that viewing volume is specified. Anything that lies within that viewing volume would be part of our scene and would be visible, and anything and everything lying outside that viewing volume would be clipped. After this point, the perspective division is performed by dividing coordinate values by w to produce the normalized device coordinates. And this is when our idea of specifying w to be equal to 1 really comes handy, because when w would be 1, dividing by w would be resulting in the same x, y, z that we started off without having homogenized our coordinates. Finally, the transformed coordinates are converted to window coordinates by applying the viewport transformation. We can manipulate the dimensions of the viewport to cause the final image to be enlarged, shrunk, or stretched. We might correctly suppose that the x and y coordinates are sufficient to determine which pixels need to be drawn on the screen. However, all the transformations are performed on the z coordinates as well. This way, at the end of this transformation process, the z values correctly reflect the depth of a given vertex. And one use of this depth value is to eliminate unnecessary drawing. OpenGL can use this information to determine which surfaces are obscured by other surfaces and can then avoid drawing the hidden surfaces. We have talked about the concept of surface normals and vertex normals. we'll be making use of these in order to identify which object surfaces are away from our viewpoint, and they are poised in such a manner that they are hidden behind certain other objects or certain other surfaces. In that case, such surfaces which are hidden behind other surfaces, they can be avoided, and we do not need to render them. We do not need to compute anything for those surfaces. Only the surfaces that would be contributing towards the final view, the final scene that we want to display, those should be considered whenever we are transforming. As we have probably discussed by now, we need to know a few things about matrix mathematics to get the most out of this lecture. As we have already learned from our previous lectures, different types of matrix manipulations we have also already covered. This is the time when we are going to make use of that knowledge. If you need to brush up, better do that now. We are going to continue with a simple example, which would be for drawing a cube. This example draws a cube that's scaled by a modeling transformation. You'll be seeing in the next figure. The viewing transformation, GLU look at, positions and aims the camera towards where the cube is drawn. A projection transformation and a viewport transformation are also specified. The rest of the section explains the transformation commands that it uses. This is the transformed cube that we shall be drawing. You are amazed to look at it and saying that, oh, is that a cube? Well, that actually is, but it has been scaled in a specific manner such that it is cutting the looks of a block, which is rectangular and not cubical. We'll get to see how we have reached this image. Let's start with the example, the transformed cube. We include the gl.h, glu.h and glut.h. Void, init void. We start with gl clear color, all zeros. GL shade model, specify the bitmap, the bit mask GL flat. Void display void, GL clear using GL color buffer bit. GL color 3F111. GL load identity, GLU look at 005 000 010. GL scale F 1.0, 2.0 and 1.0. Glut wire cube 1.0. GL flush. The next is void reshape using the arguments integer w and integer h for width and height. GL viewport 0, 0, GL size I w, w typecasted as GL size I, h typecasted as GL size I. GL matrix mode, GL projection, GL load identity, GL frustum, minus 1.0, 1.0, minus 1.0, 1.0, 1.5, 20.0. GL matrix mode, GL model view, integer main using integer argc and char pointer argv, glut init ampersand argc comma argv, glut init display mode, glut singer or glut RGB, glut init window size 500 comma 500, glut init window position 100 comma 100. Note the size and position. Glut create window argv of 0. Call to init, call to glut display func display, glut reshape func reshape, glut main loop return 0. We are going to start with the discussion on viewing transformations specified over here. Recall that the viewing transformation is analogous to positioning and aiming a camera at the desired scene. In this code example, before the viewing transformation can be specified, the current matrix is set to the identity matrix with GL load identity. This step is necessary. If we don't clear the current matrix by loading it with the identity matrix, we continue to combine previous transformation matrices with the new one that we supply. This is an important aspect that we need to note, that if we don't want our previous transformations to have an impact on our current, we better clear our matrix. And clearing the matrix is most effectively and easily done by loading the identity matrix. The identity matrix would have its leading diagonal all ones and all other values would be all zeros. We have already talked about this matrix being of size 4 by 4. In some cases, we do want to perform such combinations, but we also need to clear the matrix sometimes. In the example, after the matrix is initialized, the viewing transformation is specified with GLU lookat. The arguments for this command indicate where the camera or the eye position is placed, where it is aimed, and which way is up. And all these need to be specified before we start shooting, before we start snapping. The arguments used here place the camera at 0, 0, 5. Aim the camera lens towards 0, 0, 0 and specify the up vector as 0, 1, 0. The up vector defines a unique orientation for the camera. So we have specified the camera to be placed at a specific position and its lens looking towards a specific point, in this case the origin, and we have also specified the up vector, which tells us that this would be a unique position for the unique orientation for the camera. If GLU lookat was not called, the camera has a default position and orientation. By default, the camera is situated at the origin and points down the negative z-axis and has an up vector of 0, 1, 0. In the example, the overall effect is that the GLU lookat moves the camera 5 units along the z-axis. As I said earlier as well, that we can use the default positioning and orientation of camera as well, but we have the option of changing it as desired. So in this case, we have tried changing the position of the camera. Instead of leaving it at the origin, we have tried to move it 5 units along the z-axis, so that now we can look at the origin. We are staying away from the origin and we are looking at the origin, although we are on the same axis, the z-axis. Next, we are going to talk about the modeling transformation. We use the modeling transformation to position and orient the model. For example, we can rotate, translate, or scale the model, or perform some combination of these operations. In the example, GL scale F is the modeling transformation used. The arguments for this command specify how scaling occurs along the axes. If all arguments are 1.0, command has no effect. In example, the cube is drawn twice as large in the y direction. If you go back and look at the arguments for this command, GL scale F, you would realize that the y coordinate is specified to be 2.0. If we have all the 3 coordinates as 1.0, that would mean that all the 3 scaling factors are 1.0. That would not have any impact on the shape of the object. But when we say we are going to have y doubled, we are going to elongate in the width. And that's what we did, and that is why the shape of the cube that we saw earlier on. Thus, if one corner of the cube had originally been at 3.0, 3.0, and 3.0, that corner would wind up being drawn at 3.0, 6.0, 3.0. The effect of this modeling transformation is to transform the cube so that it isn't a cube but a rectangular box. Now you can change the GLU lookat call in the example to the modeling transformation GL translate F with the parameters 0.0, 0.0, and minus 5.0. The result should look exactly the same as when we used the GLU lookat. Why are these two effects the same, or the two commands have the same effect? Can you guess? Well, if we decide to move the camera away from the scene, or if we decide to move the objects away from the camera, the overall impact would be the same. That is why these two commands would be giving us the same effect ultimately. Note that instead of moving the camera with the viewing transformation so that the cube could be viewed, we could have moved the cube. This duality in the nature of viewing and modeling transformations is the reason why we need to think about the effect of both types of transformations simultaneously. So we cannot do that, okay, let's worry about modeling only first and then we'll worry about the viewing. Whatever we do in terms of modeling our objects or specifying different views for it, these work in conjunction with each other, producing the ultimate resultant. So if we are going to make use of one function to move the camera away, it may have the same impact as would be another function which would be used to transform or translate our object away from the camera. It doesn't make sense to try to separate the effects, but sometimes it's easier to think about them one way rather than the other. This is also why modeling and viewing transformations are combined into the model view matrix before the transformations are applied. So since the two types of transformations cannot be separated from each other because of the effects that they have at the ultimate view, these have been actually combined in one step, the model view matrix. The model view matrix takes care of the modeling and the viewing transformations that we specify. So all the modeling and viewing transformations that we specify would be combined together in one step in all those stages that the vertices have to go through before they finally get displayed as an image on the screen. Also note that the modeling and viewing transformations are included in the display routine, along with the call that's used to draw the cube, the glut wire cube. This way, display can be used repeatedly to draw the contents of the window if, for example, the window is moved or is uncovered, and we have ensured that each time the cube is drawn in the desired way with the appropriate transformations. So having coupled this with the display function, whenever display routine would be called, which would be called whenever our window is resized or reshaped or was already behind a window and is now uncovered, the redrawing would take place and our modeling and viewing transformations would be effective right there and then. The potential repeated use of display underscores the need to load the identity matrix before performing the viewing and modeling transformations, especially when other transformations might be performed between calls to display. Next is the projection transformation. Specifying the projection transformation is like choosing a lens for a camera. We can think of this as determining what the field of view is and therefore what objects are inside it and to some extent how they look. Projection is the way we project our model to be seen. This is equivalent to choosing among wide-angle, normal, and telephoto lenses. For example, with a wide-angle lens, we can include a wider scene in the final photograph than with a telephoto lens. If we want to include a larger group, we definitely would be interested in using a wide-angle lens when we are photographing. Or if we want to have a close-up of a specific person, maybe in the whole mob, we would be interested in a telephoto lens. So what we want out of the available model or out of the available objects in our scene to be displayed at one point in time or the other, that needs to be decided. And this decision is made when we are specifying the projection transformations. How our model is going to be projected. What would be the look that we would be generating from this collection of objects forming our model. But a telephoto lens allows us to photograph objects as though they are closer to us than they are actually in reality. In computer graphics, we don't have to pay a lot of money for a 2000 millimeter telephoto lens because we can do the same only specifying specific parameters passed to a command. What we have to do is we can only specify some smaller number for our field of view and achieve the same impact that we can achieve using a telephoto lens in reality when we are photographing. In addition to the field of view considerations, the projection transformation determines how objects are projected onto the screen as its name suggests. Two basic types of projections are provided by OpenGL, along with several corresponding commands for describing the relevant parameters. One type is the perspective projection, how we see things in our daily life. We have talked about perspective projection being more natural. For example, railroad tracks. If we are trying to make a realistic picture, we'll want to choose perspective projection, which is specified with the GL frustum command in this code example. Orthographic projection is used in architectural and computer-aided design applications. Before GL frustum can be called to set the projection transformation, some preparation needs to be made. As is shown in the reshape routine in the given example, the command called GL matrix mode is used first with the argument GL projection. Now, this indicates that the current matrix specifies the projection transformation. The following transformation calls then affect the projection matrix only. As we can see, a few lines later, GL matrix mode is called again, but this time with argument GL model view as its parameter. This indicates that succeeding transformations now affect the model view matrix instead of the projection matrix. Please note that GL load identity is used to initialize the current projection matrix so that only the specified projection transformation has an effect. Effective use of GL load identity. Wherever we require that the next transformation should only be applied and the impact of the previous transformations that might have already been applied to our matrix, that should be nullified, we call GL identity matrix to initialize it, so that the next step would be performed and we come up with our composite transformation matrix that would be ultimately applied to the vertex and then resulting in transformed vertex. And that transformed vertex would be used for actual image making and displaying of the scene. Now, GL frustum can be called with arguments that define the parameters of the projection transformation. In this example, both the projection transformation and the viewport transformation are contained in the reshape routine, which is called when the window is first created and whenever the window is moved or reshaped. This makes a lot of sense because both projection of the width and the height aspect ratio in the viewing volume and applying of the viewport relate to directly the screen and specifically to the size of the aspect ratio of the window on the screen. Change the GL frustum call in the first example that we've seen to the more commonly used utility library routine GLU perspective with parameters 60.0, 1.0, 1.5 and 20.0. This experiment with different values, especially for the FOV field of view, near and far plane, is going to give you some very interesting results. So folks, our discussion about this example that we have taken and talking about the viewing and modeling transformations is not complete yet. We will be continuing from where we have terminated today, but for the moment let's call it a day. Next time we'll be continuing from this point and we'll try to establish a better concept of making use of the viewing and modeling transformations to come up with interesting scenes. तब तक के लिए इजाज़त दीजिएगा. फ़ी अमान अल्लाह.